Limitations of Bohr's theory. This theory is applicable to hydrogen-like atoms only. Hydrogen-like atoms means atoms are having one electron, like lithium double plus, beryllium triple plus. If number of electrons are more than one, in that case, this theory is not applicable. Another point, in the spectrum of H atom, certain spectral lines are made up of several closed lines with different frequencies. And this fine structure could not be explained by this model. Next point is, it does not tell why one should choose the circular orbits only and not the elliptical, though elliptical orbits are also possible. And if electrons exhibit wave properties, so we know that anything that represents or that exhibits wave properties, its position can't be determined exactly. Then how one can define the orbits in such accurate way? And next point is, this theory does not tell the relative intensities of various spectral lines. And apart from that, further splitting of spectral lines in magnetic field and in electric field could also not be explained by this theory. So these points tell the drawbacks of Bohr's theory. Now let's define some important terms. Excitation energy. It is the minimum amount of energy that is required to promote an electron from its ground state to higher energy level or orbital. So for hydrogen atom, first excitation energy means, suppose as we know, E1 equal to minus 13.6 electron volt and E2 is equal to minus 3.4 electron volt. So first excitation energy will be the difference of the two. So first excitation energy will be equal to minus 3.4 minus of 13.6, that will be equal to 10.2 electron volts. Similarly, second excitation energy will be equal to, since E3 has energy minus 1.51 electron volts, so difference of the two, minus 1.51 minus 13.6 will give 12.09 electron volt. Now, let's define ionization energy. So the amount of energy required to liberate the most loosely bound electrons from the outermost shell of an isolated gaseous atom. So for hydrogen atom, we consider here E1, which is minus 13.6 electron volt, and highest here level n equal to infinity, where energy will be zero. So difference of the two, so that is E infinity minus E1 will be ionization energy, which will come out to be 13.6 electron volt. Now consider excitation potential. The energy needed to take the atom from its ground state to an excited state is called the excitation energy of that excited state, and the potential difference through which an electron should be accelerated to acquire the value of excitation energy is called excitation potential. So here first excitation potential will be equal to minus 3.4 minus 13.6. Unit will be volt this time. This is same as first excitation energy, except here earlier it was minus 3.4 electron volt and this was also minus 13.6 electron volt, but now it is only in volt. So it will be 10.2 volt. Similarly, second excitation potential will be equal to minus 1.5 but minus of 13.6, and that will be equal to 12.09 volt. Now let's define ionization potential. Ionization potential is the difference between corresponding to the energy in electron volts that is just sufficient to ionize a gas molecule or to remove an electron completely from the atom. Means potential required to remove an atom. Sorry, potential required to remove an electron from the atom. So here, ionization potential of hydrogen, if we define, so it will be equal to 0 minus 13.6, which is 13.6 volt. If you remember, the energy of first level E1 equal to minus 13.6 electron volt, and for E infinity it is 0. So here the same is done. Electron is moved from this level to infinity. So first it was excited to that energy level, and then potential difference applied to make electron capable to leave the atom will be equal to ionization potential, and that is shown here. Thank you for watching.